Hi, my name is Shahnawaz. In this lecture, we'll study the varieties and locally closed varieties. But before that, we'll define uh, irreducible components. I mean, if suppose we have a polynomial, say xy, in the polynomial ring, two variables with a field k, then the algebraic set, I mean the zero set of xy. So we can write this as the union of two coordinate axes, i.e. we can write this algebraic set as the zero set of x union zero set of y. So if we look at this polynomial xy equals 0, it is solutions are either x is 0 or y is 0. So geometrically this means that the zero set of this polynomial xy is the zero set of x union the zero set of y. So such algebraic sets which can be written as the union of smaller algebraic sets are called reducible. Otherwise we call them um, irreducible. So we have this definition. So I mean, we show that every affine algebraic set can be written in a unique way as a union of irreducible algebraic sets. So that is our goal. So we have this definition first. So we call a topological space, say X, a reducible topological space. So a topological space X is called reducible. So if we can write X as the union of the sets x1 union x2, where x1 and x2 are closed proper subsets of x, where x1 and x2 are closed proper subsets of x. So in this case we call x a reducible topological space. Otherwise x is called irreducible. So now we have a following proposition. So let us suppose that x be an irreducible topological space. And suppose say U be any non-empty open subset. So then this U is dense in X. So this means the closure of U is actually equal to X. And second item is that U is irreducible. So let us prove the item first. So suppose U is not dense in X. So suppose u is not dense in X. So if this is the case, then u closure and this set X minus u, they are both closure subsets. So are both closed proper subsets of X. So one can note that. So note that we can write X as the union of the set uh, X set minus u union u closure. So this is not possible since X is mm, so this is not possible since X is irreducible. So this shows that the closure of u has to be the whole X. That is, u is done as an X. So this proves the first item. Now for second item, suppose u is reducible. So suppose u is actually the union of two smaller closed sets where u1 and u2 are closed proper subsets of u. Now what we do, say for I is equal to 1 2 we set, so for I equal 1 and 2 we set xi to be equal to the closure of ui. That means both so this closure we are taking this in X, so this is the closure of ui in X. The closure in X. So one can note here that this u is a this u is a closure subset of u. So the closure of ui in u is ui, but the closure of ui in X may not be equal to u. So that is why we set xi to be the closure of ui in X. Now note that both xi's are proper subsets of X. So since one can note here this ui, which we can write as the xi intersection u, so this is not equal to u. So that is why these are proper subsets. So also x1 union x2, this is equal to u closure, which is equal to X, because u being an open set in X, so it is dense by item first, and hence u closure is X. So this proves that this X is uh, reducible, which is not the case. So hence u is irreducible. Now, the notion of this irreducibility does not make much sense in the strong topologies. For example, the only The only irreducible sets of Hausdorff space are just the points. So this won't make much sense in the bigger topologies. I mean, the strong topologies. Now we have the definition here. So we call an irreducible uh, algebraic set so an irreducible affine algebraic set is called a closed subvariety of n is called a closed subvariety of the affine n space, and an open subset of an affine variety is called a locally closed subvariety of n. So an open subset of an affine variety is called a locally closed subvariety of n. So we have the examples. So if I look at any point in the affine space, so it is, so let us write this down. So a point P in the affine n space is irreducible. So and hence a closed subvariety. However, if we take the zero set of the polynomial xy in the affine space, sorry, this is the 2 affine space, so this is reducible. So this is reducible since the zero set of xy can be written as the union of two smaller algebraic sets. Now so we said that in the algebraic properties of the ideal of x should reflect the geometric properties of the x, I mean an algebraic set. The first instance for this is the following result. So we have a result here. So we have the proposition. So it goes like this. So an algebraic set x in the affine space is closed subvariety. So is a closed subvariety if and only if uh, the ideal of x is a prime ideal. So let us prove this. So we have the proof. Let us suppose X be a closed subvariety. So let X, which is subset of F and N space. So let us assume that this is a closed subvariety. So hence this X is not reducible. So in other words, it is uh, irreducible. So hence X is an irreducible algebraic set. Now to show Ix is prime ideal, we'll take, let's say, a product of two polynomials in Ix. Now to show Ix is a prime ideal, let us suppose that f dot g belongs to the ideal of X for some polynomials f and g in. So for some f and g in the polynomial ring in n variables. So to prove Ix is prime ideal, it suffices to prove either f is in Ix or g is in Ix. So then by decreasing property of z, so then by decreasing property of the function z, we have the zero set of fz, I mean so zero set of f dot g, it contains the zero set of, sorry, it contains the zero set of the ideal of X. So because since f dot g is in the ideal in X, so that means the ideal generated by f dot g is actually contained in the ideal of X. Now since this 0 is decreasing, so this would imply the zero set of this ideal actually contains the zero set of ideal of X. But this is same as X, since the function 0 composite I is actually the identity map. So this would imply this X is actually contained in the zero set of Fg, which is equal to zero set of F union zero set of G. So this is what we get from this, and this further implies, and hence since X is inside this set, so this would imply X is actually equal to the zero set of F intersection X union zero set of G intersection X. Now as X is irreducible, this would imply either this set is equal to X or this set is equal to X. So this would imply, so it follows that mm, so it follows that either zero set of f intersection x is equal to x, or zero set of g intersection x is equal to x. Now this would imply that zero set of f contains x, or zero set of g contains x. So this gives zero set of f contains x, or zero set of f contains not f, I mean g. Again, by decreasing property of the function z, this would imply either f is in the I mean ideal x, or g is in the ideal x. So in other words, f belongs to ideal of x, or g belongs to ideal of x. Now this proves that this ideal Ix is actually a prime ideal. Now to prove the converse, I mean if we assume Ix is prime ideal, we have to prove that this x is not reducible. So this is same as to prove if Ix is not prime ideal, then x is not irreducible. So we prove the converse using contrapositive. So to prove the converse, we prove the contrapositive. Assume x is contained in A is not closed subvariety. So actually we have to prove if Ix is prime ideal, then this x is a closed subvariety. Now it suffices to prove if x is not closed subvariety, then X is not prime ideal. So that is what we mean by contrapositive. So we are assuming that this x is not a closed subvariety, and let x be equal to x1 union x2. Since this is not closed subvariety, this would imply x is reducible. So we can write x as the union of x1 and x2, where x1 and x2 are closed proper subsets of x, or algebraic subsets. So for algebraic subsets x1 and x2 which are properly contained in x. So then again, by decreasing property of the function I, we have ideal of x1, it contains ideal of x, and ideal of x2, it contains ideal of x. So if this is the case, this means there exists f1 and f2, I mean two polynomials in the polynomial ring, such that f1 is in ix1 but not in ix. Similarly, f2 is in ix2 but not in x. So this implies that there exists two polynomials, say f1 and f2, in the polynomial ring in n variables, such that f1 is in the ideal of x1 but not in ideal of x, and f2 is in ideal of x2 but not in ideal of x. So this further implies that this f1 dot f2, product of f1 and f2, vanishes at each point of the union of x1 and x2. So this would imply that f1 f2 vanishes at each point of x1 union x2, which is equal x. That is the product f1 f2. This is actually in the ideal of x. So what we proved f1 which is not in I x1, f2 which is not in I x2, and we proved f1 which is not in x and f2 which is not in x. So this implies f1 f2 is in ix. So this is possible only if this ix is not prime ideal. So this shows that uh, ix is not prime ideal, because an ideal P is prime ideal if whenever AB is in P. This would imply either A is in P or B is in P, or if A is not in P and B is not in P, this would imply AB is not in P. So both the situations would imply the P is prime ideal. So what we proved here, we proved that this product f1 f2, this is in ix, but neither f1 is in ix nor f2 is in ix. So this means that the ix is not prime ideal. So hence, if ix is prime ideal, this would imply this x is actually a closed subvariety. So this proves the result. So this proves the result. Now we have a remark here. So if we look at the statement of this result, uh, it says that an algebraic set X is closed subvariety if and only if it is ideal is prime ideal. So actually this statement is equivalent to the fact that if X is a closed subvariety if and only if X is some zero set of X is zero set of prime ideal. So this statement of above proposition is equivalent to saying that an algebraic set X in the affine n space is closed subvariety um, if and only if this x is this x is equal to 0 set of p for some prime ideal p in the polynomial ring x1 through xn. So the reason for this is that every prime ideal is a radical ideal. So for example, um, by above result, x is irreducible if and only if the ix is a prime ideal. Say ix is p, where p is a prime ideal. So this would imply, so this statement is equivalent to the fact that x is irreducible if and only if x, which is equal to the 0 set of I of x, which is same as 0 set of now I of x, the prime ideal. So that is what I mean we were trying to say. That means if x is closed subvariety if and only if this x is a vanishing set of some prime ideal. Now we have a consequence of this result. So it says that if f is a polynomial in the polynomial ring in n variables, so if this polynomial is irreducible, then the 0 set of f is also irreducible. So let us prove this. So the proof goes like this. So let f be a polynomial in the polynomial ring in n variables over the field k such that f is irreducible. Now this polynomial ring be a unique factorization domain. This would imply the ideal generated by f is actually a prime ideal. So now the polynomial ring being a unique factorization domain, the ideal the ideal generated by f is a prime ideal. Now this being the prime ideal and knowing the fact that the prime ideals are radical ideals, so this would imply, so since the ideal generated by this is prime, we have the radical of the prime ideal f is actually the ideal f. Now by Null's tensors we have, so Null's tensor says that the ideal of the 0 set of and the ideal generated by J is actually equal to the radical of J. I mean, this composition over here, this goes, sorry, the composition I composer. So this goes from the vanishing sets of ideals to the radical ideals. So therefore, by null tensors, the ideal f is actually equal to the radical of f, which is same as the ideal of the zero set of the ideal generated by f. So therefore zf is irreducible, because this follows from the above fact. So therefore, because if ideal of some set is zero, sorry, if ideal of some set is prime ideal, then that algebraic set has to be irreducible. So therefore, the set is irreducible. So this proves the result.